Welcome back to Next Dream 1, 2, 3. I am Akshay. Yes. And today we are continuing our linear algebra top important questions with shortcuts part 2. In this session, we are focusing on exam oriented high weightage questions that are especially useful for Kset 2026, AP set, TS set, and Maharashtra set 2026. We will discuss the question with a clear conceptual approach along with smart shortcuts and time saving techniques wherever possible. Our main focus will be on important concepts such as matrices, rank, nullity theorem, and linear transformations, vector spaces, system of linear equations, and other frequently tested areas of linear algebra. The aim is not just to get the answer, but to understand how to identify the correct method quickly in the examination. So keep your pen and paper ready. Try each question yourself first, then compare your approach with the shortcut method. Let's start part 2 of linear algebra, top important questions with shortcuts. All the best and let's crack these questions together. Our first question number 10. See, in 10th question, a 3 by 3 matrix has a characteristic polynomial x minus 2 square x minus 3. The matrix is diagonalizable if and only if. Okay, they given 4 options. In the geometric multiplicity of eigenvalues 2 is 1. The geometric multiplicity of eigenvalues 2 is 2. The geometric multiplicity of eigenvalue of 3 is 2. The matrix has 3 distinct eigenvalues. Okay. See, you should remember what is the characteristic polynomial is given x minus 2 square, x minus 3. It can be written as x minus 2. This can be written as 2 times like this, x minus 2 and x minus 2 and x minus 3. From here, eigenvalue is equal to eigenvalues. What are the eigenvalues we get? 2 comma 2 comma 3. You should remember one thing: if the matrix is diagonalizable, algebraic multiplicity should be equal to geometric multiplicity. This is very important. Okay, what is algebraic multiplicity? Algebraic multiplicity of 2. See, there are eigenvalues 2 and 3. Okay, algebraic multiplicity tells us how many times eigenvalue is repeated. Okay, here eigenvalue 2. Okay, the eigenvalue of 2, geometric multiplicity of eigenvalue 2 is equal to how many times it is repeated? 2 times. Okay, geometric multiplicity of 3, the matrix 3 is only 1. Okay, if the matrix is diagonalizable if and only if algebraic multiplicity of 2 is same as geometric multiplicity of 2. Okay, because this is the only algebraic multiplicity of 3 is, it is only 1. Algebraic geometric multiplicity also only 1 we get here. Okay, then if you check the options, geometric multiplicity of eigenvalue 2 is 1. No, is wrong option. The geometric multiplicity of eigenvalue 2 is 2. Yes, it is correct option. The geometric multiplier of 3 is 2 because geometric multiplier of 3 is 1, but is given 2, is wrong. The matrix has 3 distinct eigenvalues. No, because it is repeated eigenvalues. Okay, distinct eigenvalues, there is no distinct eigenvalues. This is also wrong. That means our option is only B. B is the only correct option for this question. Next question number 11. Okay, let's try this question. Let v1, v2, v3 be linearly independent vectors in R5. Which of the following is always true? Okay, they given 4 options. Okay, the set contain v1, v2, v3 spans R power of 5. Okay, R of 5. And the set v1, v2, v3 can be extended to a basis of R5. Okay, the set contain v1, v2, v3 is a basis of R5. The dimension of span of v1, v2, v3 is equal to 5. Okay, let's check this question. This is, see, you have to clear about concept of linearly independent. Okay, if you clear with the concept of linearly independent, see, we have a direct shortcut or direct result. Okay, regarding this, let's analyze question one by one. Okay, first I will write what is the result. Okay, we have a direct theorem, that is basic extension theorem. Basic extension theorem. What this theorem tells us, any linearly independent set in a finite dimensional vector space can be extended to a basis of that vector space. This is a very important theorem, you should remember. Okay, any linearly independent set in a finite dimensional vector space can be extended to a basis of that vector space. Okay, let's discuss first option. See, this is the set which contains three vectors v1, v2, v3, spans R5. Okay, but we know that these three vectors cannot span 5-dimensional vector, because see, this set contain only three vectors, but what is dimension of R power of 5? 5. Okay, this 5-dimensional vector space, this R power of 5 is a 5-dimensional vector space. These three sets, these three vectors, the vectors of v1, v2, v3, this cannot span a 5-dimensional vector space. Okay, see, if you write down the given three vectors, okay, cannot span a 5-dimensional space. Okay, you should remember, if you want to say this option is correct, it should be span R power of 5. Okay, but here this set contain only three vectors. This cannot form a 5-dimensional vector space. This is absolutely wrong. This is the wrong option. And B is the correct option, because according to the theorem, basis extension theorem, v1, v2, v3 can be extended to a basis of R power of 5. This is correct. This option is correct. And C, v1, v2, v3 is a basis of R power of. See, there is a difference between extended and only basis. Okay, understood. This is wrong option actually. If they given extended word, then this is also correct. But if they not mentioned that this word extended, okay, that's why this is wrong. Okay, and if you want, you can write down a basis R power of 5 must contain exactly 5 linearly independent vectors, then only this forms a basis. Okay, and D option, what is D option? Is dimension of span of v1, v2, v3. But dimension of span of v1, v2, v3, what is this? This contain only three vectors. The dimension of span of v1, v2, v3, that is equal to 3. This is not equal to 5. Okay, but is given 5. This is also wrong. Our option is only B option. Okay. Okay, if you want, you can write down one direct result like this. The same theorem you can write down as a short form. Okay, linearly independent set plus dimension is always extended to basis. Okay, understood. If you observe that in this question they given three vectors. Okay, this result you should remember. In our question is given three linearly independent vectors. Okay, in R power of 5. Okay, then it is extended by two vectors to get what? To get a basis. Okay, you should remember this, very important one. And this is a question, 12th question. Let u is equal to this and w is equal to, the set is given like this. What is dimension of u intersection W. Okay, this is also important one. Okay, just try this question once. What is the set U is given? X comma Y comma Z comma W. Okay, such that X plus Y is equal to 0, Z minus W is equal to 0. And W is given X comma Y comma Z is W, such that X minus Y is equal to 0, Z plus W is equal to 0. Okay, you should understand, first we have to find U intersection W. Okay, before finding dimension of U intersection W, we should find what is U intersection W. See, what is the meaning of intersection? Intersection is nothing but common, okay, common elements, okay, common portion. That is nothing but it indicates intersection. Okay, first we solve the conditions. What are the conditions given? X plus Y is equal to 0. Okay, from this I will write as X equal to minus Y. Okay, from this Z minus W is given. Okay, I will use this. I will keep here. See here given Z minus W is equal to 0. From this I will get Z is equal to W. Similarly from here I will get X minus Y is equal to 0. That implies X equal to Y. Okay. See, if you observe that this side is same. That means this side is also same. That means minus Y is equal to Y equal to 0. Sorry. One minute. Minus y equal to y, that implies what? Y equal to 0. If y is equal to 0, x also equal to 0. Okay, if you simplify this, from here we get z is equal to minus w. If you similarly here also, here the both side is same, then RHS side w is equal to minus w, that indicates what? W is equal to 0, because it is, if you shift minus w this side, it becomes 2w, that is equal to 0. W is equal to 0. If W is equal to 0, Z also equal to 0. Okay, then if Z is equal to 0, W is equal to 0, then what is U intersection W? We get X equal to 0, Y is equal to 0, Z is equal to 0, W is equal to 0. That's it. Then it is a zero set, zero vector. Okay, zero vector. It is a zero vector. Okay, the intersection contain zero vector, then dimension of U intersection W, that is equal to 0. Okay, then our option is A. A is our correct option. Okay, whenever they asking related to intersection, first solve simplify like this. Okay, simplify. Find whatever the variables x, y, z, w. Find all these variables. Okay, this is the method. And let's move to next question. Question number 13th. Let T is mapping from R square to R square. Okay, means R2 to R2 be given by T x comma y is equal to 2x plus y comma x plus 2y. If B is equal to 1 comma 1, 1 comma minus 1 is the basis of R square. The matrix of T relative to B is diagonal. What are its diagonal entries? Okay, they given 4 options. Okay, let's we have to find diagonal entries. See, this is a linear transformation. You should know how to write in matrix form. Okay, matrix transformation. They provided what? Basis. Okay, is a basis of R square. This is not a standard base. Okay, 1 comma 1 and 1 comma minus 1 is not a standard basis. Okay, sorry. Okay, first we have to find matrix form. See, you should understand. First try this question. Okay, see, this is a transformation. Okay, see, this is a domain R2, this is a codomain R2. Okay, domain is also R2, codomain is also R2. For the both the R2, R2 and R2, okay, what is the basis is given 1 comma 1, here also 1 comma minus. For this also basis is 1 comma 1, 1 comma minus 1. Okay, we have to apply transformation to this basis. Okay, t of 1 comma 1, that is equal to, okay, this is a x, this is a y. Okay, you substitute these x and y values in given transformation. Okay, what we get? 2 plus 1 comma 1 plus 2, that is equal to 3 comma 3 we get. Okay, 3 comma 3. And next, t of 1 comma minus 1. Okay, that is equal to, you substitute here, we get 2 minus 1, 1 minus 2, that is equal to 1 minus minus 1. See, these two elements, okay, after applying transformation to this, okay, these are the images, these images is present here, 3 comma 3, 1 comma minus 1. Okay, this 3 comma 3 can be written as, okay, alpha times of basis 1 comma 1 plus 1 comma minus 1. Okay, you should write like this. Here beta you take. Okay. Next here gamma 1 comma 1 plus delta 1 comma minus 1. If you want, you can write. You can give any symbols, no problem. Okay, here I am using a symbol alpha beta. If you want, you can take v1, v2, okay, v3, v4, like that also, no problem. Okay, I can write like this. Okay, then you simplify this. We have to find alpha beta. What is alpha and beta? That is our main intention here. Okay, finding alpha and beta. Let's find alpha beta here. Here 3 comma 3 is equal to, if you multiply alpha inside, we get alpha comma alpha plus beta comma minus beta. Okay, that is we get alpha plus beta. Okay, comma alpha minus beta 3 comma 3. Okay, if you observe that alpha plus beta is equal to 3, alpha minus beta is equal to 3. Okay, you simplify this. What we get? Alpha minus beta is equal to 3 means alpha we get 0. Okay, if alpha is 0, okay, what is the beta we get? If alpha is 0, beta we get 3. Okay, wait, I did mistake here. Alpha plus alpha 2 alpha, 3 plus 3 6. Okay, alpha we get 3, not 0, sorry. Okay, when alpha is equal to 3, okay, beta we get 0. Okay, in this situation, similarly, okay, we get 1 comma minus 1, that is equal to gamma minus gamma plus delta gamma plus gamma here. Okay, delta minus delta, that is equal to, okay, gamma plus delta, gamma minus delta, 1 comma minus 1. Okay, gamma plus delta equal to 1. Compare the values. Okay, gamma minus delta equal to minus 1. Then we get here 2 gamma is equal to 0. Gamma equal to 0. Okay, if gamma is equal to 0, okay, delta equal to 1. Okay, then you should write on matrix form. Okay, I will denote the matrix with transformation T with the basis B. that is equal to our basis. What is our basis? C. If you write alpha, beta, gamma, delta, that is equal to, what is alpha? 3. What is beta? 0. What is gamma? Delta? 1. Okay, they are asking diagonal entries. What are diagonal entries here? 3 and 1. 3 comma 1. Our option is A. A is the correct option here. Okay. Okay. See, there is a shortcut also is there. See, if you observe clearly, these are not a standard basis. These are not a standard basis, but still there is a shortcut. See, this is a process to point the, it may be standard basis or any basis. This is the standard way to solve the matrix transformation. Okay. We have to find the matrices, okay, by using transformations. Okay. See, whenever you should remember, this is the shortcut. If the given basis, the given basis vectors are eigenvectors, okay, simply calculate T of V1, that is equal to lambda 1 V1, T of V2, that is equal to lambda 2 V2. Okay, then our matrix, so with the basis we get lambda 1 0 0 lambda 2. Okay, see, if you observe that in this question here, T of 1 comma 1, okay, this is what we get 3 comma 3, correct? T of 1 comma 1 we got 3 comma 3. It can be written as, take 3 outside, we get 1 comma 1. See, this is a lambda 1, sorry, this is a V1 vector, this is also V1. Okay, lambda 1 is 3. Okay, similarly T of 1 comma minus 1. Okay, after simplifying, what we get here, what we got here, 1 comma minus 1 only. 1 comma minus 1 only. That is nothing but simply can be expressed 1 into 1 comma minus 1. Okay, if it is the case, our matrix becomes, my matrix becomes lambda 1. It is lambda 1, this lambda 2. 3, 1, 0, 0. Okay, this is a direct shortcut. Okay, you can verify. Okay, if this will works, go with this method. Okay, this shortcut. Otherwise, you can go with normal traditional method. Okay, this is the 14th question. Let it is R3 to R3 be defined by, this is the transformation for which value of lambda is t is not invertible. Okay, say if you observe that they not provided any basis, they not provided any basis. If they not provided any basis means you consider basis as standard basis. Okay, you consider basis as standard basis. Okay, for R3, what is standard basis? 1 comma 0 comma 0. Okay, 0 comma 1 comma 0, 0 comma 0 comma 1. These are the standard basis. Okay, basis of R3. These are the standard basis of R3. Okay. See, and one more thing, whenever if it is standard basis, there is a shortcut, direct shortcut, no need to apply standard method. Okay, there is a direct shortcut method here. What is shortcut method here? See, observe here, carefully observe. My transformation matrix, I will give you a name for this matrix, so just take a. Okay, see, it has a 3 variables. See, it is R3 to R3. That means my matrix is 3 by 3 matrix. Okay, and first how to write the first row. See, this is the first one. Okay, x plus 2y plus 3z. Okay, just take the coefficients. X coefficient is 1. Here y coefficient is 2. Z coefficient is 3. That is our first row. Here, see, there is no x here. You just write as 0x. Okay, 0. Here 1. This is 4. Okay, I hope this is clear. Okay, next here 5, 6 lambda. Okay, see they given which value of lambda is t is not invertible. Okay, t is, see if t is invertible, always remember, okay, the determinant of the matrix, okay, should be not equal to 0. Okay, if t is invertible, determinant of a is not equal to 0, but is they saying is not invertible, it is not invertible means, if they saying it is not invertible means determinant of a is equal to 0, that is the meaning. Okay, that means simply find beta of a is equal to 0. Okay, you get 1 2 3 0 1 4 5 6 lambda, that is equal to 0. Expand this, we get 1 lambda minus 6 4s are 24 minus 2, okay, minus 20 plus 3 minus 5 equal to 0. Just simplify, lambda minus 24 minus minus plus 40 minus 5 3 is a 15, that is equal to 0. Okay, let's calculate all these values. Okay, they given minus 24, okay, plus 40 and minus 15, that is nothing but 1. Okay, this is nothing but 1, lambda plus 1 equal to 0, then lambda equal to minus 1. Okay, lambda is equal to minus 1, that is my answer is minus option A. Option A is the correct option for this question. Option A is the correct option for this question. Okay, let's discuss 15th question. I discuss 15th question. Try this question. Okay, pause the video and try yourself. Okay, what is given here in this? Let A be n by n matrix. Which of the following statements is always false? Okay, always false. This is very important. It is n by n matrix. Rank of A is less than or equal to minimum of m comma n. This is always true. Always true. This is the standard result actually for rank. Okay, rank of the matrix is always true. Rank of A is equal to rank of A transpose. This is also always true. Okay, this is also always true. And come to option C, the row rank of A, okay, can differ from the column rank of A. No, see, we know that, okay, for every matrix A, okay, row rank of A, there is always equal to column and rank. Okay, this is a standard result, but they given differ means different. This is not true. This statement is false. This statement is not true. Okay, if rank of A is good and the number of A's are linearly independent, is always true. Always true. This is always true. Okay, if rank of A is equal to n, okay, the number of the columns of A are linearly independent. This is always true. Okay, C option. This is a false. They are asking only false. This is the our correct option. Just C is the correct option for this question. Let's move on to next question. Question number 16. For which values of k does the homogeneous system at k minus 1x plus y equal to 0, k plus k minus 1 y equal to 0 have a non-trivial solution? Okay. Okay, let's try yourself by pausing the video. Okay. See, what are the conditions are given here? K minus 1 x plus y equal to 0. Okay, x plus k minus 1 y equal to 0. If you observe that these two equations are homogeneous, that means RHS side is 0. If RHS side is 0, these equations, this system of equations is a homogeneous. They clearly mentioned in the question also. Even if they not mentioned, these are the homogeneous equations. Okay, and one more thing, if it is the given, if it is homogeneous system, I have a non-trivial solution. You should always remember, okay, the coefficient matrix, okay, determinant, okay, det of coefficient matrix is always equal to 0, must be 0. Okay, this is the result you should remember. If it is non-trivial solution, okay, determinant of the quotient matrix must be 0. This is the result, standard result you should remember. Okay, if you write, if I will give a name A, okay, x quotient is k minus 1, here y quotient is 1, x quotient is 1, k minus 1. Okay, just find the det of A. Okay, this value should be equal to 0. Okay, then we get k minus 1 square minus 1 equal to 0, that k minus 1 square equal to 1. Okay, then we get k minus 1 equal to plus or minus 1. If I will shift this minus 1 that side, we get k is equal to plus or minus 1 plus 1. That means I will get two values. One is plus 1 plus 1. One is minus 1 plus 1. That is I will get 2. One is 0. That means C is the correct option. K is equal to 0 or K is equal to 2. C is the correct option here. Okay. C option is the correct option for this question. Question number 16. Let's move on to next question. Question number 17. Okay, let A be a skew-symmetric n by n real matrix where n is odd, the det of A. See, if A is skew-symmetric, then order of the matrix, if order of the matrix is odd, directly the value, okay, det of A is always equal to 0. Option A is the correct. Okay, how we got this answer? See, let's discuss this. What is skew-symmetric? A transpose equal to minus A. Okay, let's apply det on both sides. We get det of A transpose equal to minus, so det of minus A. Okay, then we know that det of A transpose is same as det of A. We know the properties, det of A transformation. Okay, determinant of A transformation is same as determinant of A, and determinant of K times of A, that is equal to K power of n into determinant of A. This is one more property. Okay, by applying this property, in place of this I will written as determinant of A. Okay, if you take minus outside, it can be written as minus 1 power of n into determinant of A. Okay, say if you observe that, okay, if I will take n is odd nothing but like 1, okay, n is equal to 1 3 like that, 1 3 5 like this. Okay, if I will take n is equal to 1, for example, odd, what happens is determinant of A is equal to minus of determinant of A. Okay, that means if I will shift this side, we get 2 times of det of A equal to 0, then finally we get det of A equal to 0. Okay, like this we got answer is 0. Okay, this is the answer for question number 17. Okay, let's discuss 18th question. Which of the following is necessarily true about the eigenvalues of 3 by 3 real orthogonal matrix A with determinant of A equal to 1? Okay, first read what are the options they provided. Okay, let's understand options one by one. Option A, at least one eigenvalue equals 1 and all eigenvalues have absolute value 1. And B option, all eigenvalues are real. Option C, at least one eigenvalue equals minus 1. And option D, all eigenvalues equal to 1. Okay, these are the options are given. Okay, here are given. Okay, let's discuss one by one. What is the given in the question, first of all? In the question they provided eigenvalues of 3 by 3 real orthogonal matrix. Real orthogonal matrix Okay. That, and also with the determinant is given, determinant of A is equal to 1, they provided. Okay. You should remember one thing. Okay. For real orthogonal matrix, every eigenvalue, okay, every eigenvalue, okay, I will give a name for eigenvalues lambda, which satisfies, okay, absolute, okay, absolute value of lambda equal to 1. Okay, this is a very important, this is very important. Okay. Okay, then we check options. At least one eigenvalue is equal to 1 and all the eigenvalues absolute value 1. Yes, this is correct option. Option A is the correct. All eigenvalues are real. Real means what? What are that real? All eigenvalues are real. Okay. All eigenvalues are real is given. Okay. Let's see. See, this is nothing but modulus of lambda equal to 1. Just what is the meaning of indicator? So this is a circle actually. Okay, this is a circle. Okay, the values which are lies on this. Okay, this gives us real. But imagine, for example, two eigenvalues like e power of I theta. Okay, e power of minus I theta. These are the two eigenvalues for, I am telling for B option, e power of I theta and e power of minus I theta. Okay, if you take modulus, okay, if these are the eigenvalues, if you take modulus, you get one only. Okay, you get one only. But these are the real? No, there's no real. Okay, is not a real value. That's why this B option is wrong. Okay, if you take a C option, at least one eigenvalue is equal to minus 1. Okay, if minus 1 were an eigenvalue, then determinant of A is equal to, see, at least one eigenvalue is equal to minus 1 means they clearly mention that determinant of A is equal to 1. Okay, we know that det of A, that is equal to product of eigenvalues. Okay, then if it is the eigenvalue, at least one eigenvalue is minus 1, it should be satisfied this condition. See, determinant of is 1, then at least one eigenvalue is equal to minus 1 means, that means minus 1, okay, into minus 1, it gives minus 1. Okay, not 1. Okay, this is no sense, right? Okay, this is wrong actually. That is wrong. Option D, all eigenvalues equal to 1. No, it is also wrong. Okay, because it is a rotation matrix. I see orthogonal matrix is like a rotation matrix. Okay, it can be eigenvalues like 1 comma e power of I theta comma e power of minus I theta. Okay, not all 1. Okay, understood. It is a rotation matrix. That's why the all eigenvalues equal 1 is wrong. The statement is wrong. Only option A is only wrong. Sorry, option A only right answer for this question. Okay, let's move on to next question. Matrix A is given. Find the value of lambda for which A has eigenvalue 3 with algebraic multiplicity 3. Okay, if you observe this matrix clearly, this is upper triangular matrix. Okay, in upper triangular matrix, upper triangular or lower triangular or diagonal, okay, in these matrices, eigenvalues is same as diagonal entries. Okay, these are the shortcut. Okay, you should remember. If you observe the diagonal entries, sir, what are the diagonal entries here? Eigenvalues is equal to 3 comma 3 comma lambda. Okay, algebraic multiplicity. What is algebraic multiplicity? Algebraic multiplicity is nothing but how many times eigenvalue is repeated. Okay, algebraic multiplicity is equal to, they given in the question, algebraic multiplicity of 3 is 3. Okay, that means 3 is repeated, algebraic multiple of 3 is 3. That means the eigenvalue 3 is repeated 3 times. That means all these 3 eigenvalues are 3 only. 3 comma 3 comma 3 only. That means our lambda is also 3 only. That means option C is the correct option for this question. Okay, you should remember all this one. Okay. What is geometric multiplicity? Geometric multiplicity is nothing but how many independent eigenvector it has. Okay, that is the meaning of geometric multiplicity. And we have one famous result also whenever it is they asking related to geometric multiplicity. Okay, geometric multiplicity is same as nullity of A minus lambda I. Otherwise, n minus number of order of the matrix minus rank of A minus lambda. You should remember this. This is very important result. Okay, this is very important result. Okay. Let's move on to next question. 20th question. For matrix A, okay, which of the following statement is true? Okay. If you observe that again it is a upper triangular matrix, then eigenvalues are 2 comma 2 comma 2. Okay. And A is diagonalizable with eigenvalue 2 of multiplicity 3. Okay. To find diagonalizable, see, should remember one thing. If matrix A is diagonalizable, okay, the matrix should have all different eigenvalues. Otherwise, algebraic multiplicity is same as geometric multiplicity. If AM is equal to GM, then matrix is diagonalizable. Okay, it's not necessary that if AM is sorry, if it is diagonalizable, AM equal to GM, but you should remember this is the condition. We have to check if the AM equal to GM, then a matrix is diagonalizable. Okay, so remember this. Okay, what is AM? Okay, algebraic multiplicity. There is a eigenvalue 2. Okay, algebraic multiplicity of 2 is 2 only. Here we have to find geometric multiplicity. Geometric multiplicity is same as order of the matrix minus rank of A minus lambda is 2 here 2i. Okay, this is the lambda. Okay, n is 3 by 3 matrix 3 minus. Okay, let's find rank of this matrix. Okay, rank of A minus 2i. That means 2 minus 2 0, we get 0 0 0. Okay, then it is 0 1 1, and here we get 0 0 0. If you observe that in this wait, algebraic multiplicity is 3 not 2, because 3 times, right? It is 3 times repeated. Okay, 3 means rank of this means here linearly independent row is only 1, then rank of this matrix is 1. 3 minus 1 is 1. Okay, then geometric multiplicity of 2 is 1. If you observe that the both are not same, then A is not diagonalizable. A is not diagonalizable. If this is not diagonalizable, the given A is diagonalizable is wrong. A is not diagonalizable since the geometric multiplicity eigenvalue is 2 is less than its algebra. Yes, this is true statement. Yes, 3 distinct nothing but different, but here all are repeated only is wrong. A is diagonalizable is wrong. Only B is the correct option for this question.